Swayam Prabha. Digital India. Educated India.
Welcome to the paper on Organic Chemistry 3. We are going to study about Unit 3, Heterocyclic Compounds. In Lecture 3, we are going to study about aromaticity in 5 and 6-membered ring heterocycles. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. The topics that will be covered in this session include criteria for aromaticity. So, we are going to study about what are the basic aromatic criteria for the 5-membered heterocyclic and 6-membered heterocyclic compound containing one heteroatom. So, we will be studying about planarity requirement, 4n plus 2 pi electrons or the Huckel's rule, ring current and resonance are the 4 things we will be studying. That is a cyclic conjugated structures we will be looking at. We will also be looking at the general characteristics based on aromaticity. So, how the reactivity differs because of this aromatic nature, what is thermodynamic stability, what are the different dipole moments of saturated and other heterocyclic compounds, especially furan, pyrrole, thiophene and the pyrrolidine, tetrahydrofuran, tetrahydrothiophene, all those things we will see. We will also study about the resonance energies, bond length, electron densities and the relative reactivities. Welcome to the next session. In this session, we are going to look at aromaticity in 5 and 6-membered ring heterocycles. We will first start with the 5-membered ring heterocycles. The basic 3 compounds what we will be studying are pyrrole with nitrogen as a heteroatom, furan as oxygen as a heteroatom, thiophene with sulfur as a heteroatom. These 3 compounds show aromaticity. So, there are various criteria for aromaticity. We will look at one by one in this session. Okay. The first one is the planar structure. So, if you look at the structure of these 3 compounds, they have planar structure. So, this is the structure of pyrrole. This is our planar structure. When we talk about planar structure, the 3D arrangement or the 3D representation of this molecule is shown here. So, this is the nitrogen atom and this is the hydrogen attached to the nitrogen atom. This is one of the carbon, this is another carbon and the other 2 carbons are actually behind, and these ash color compounds are basically ash color circle or hydrogen atoms. So, if you look at the structure here, it is highly planar in nature. So, that tells like pyrrole is having planar structure. So, that means this is one of the criteria for being aromatic in nature. The next one is furan. So, when we look at furan, furan is also having the same planar structure. So, this red color atom is oxygen and the gray color one is carbon. The ash color one is hydrogen. So, this is where we can actually see the planar nature of the furan ring. And similarly, when we talk about the thiophene, this yellow color atom is the sulfur atom, this is thiophene. So, thiophene is also having the planar structure. So, what we can say is all the 3 heterocycles, that is the 5-membered heterocycles, pyrrole, furan and thiophene, they have a planar structure. The next one what we are going to look at aromaticity is the 4n plus 2 pi electron rule, that is the Huckel rule. According to Huckel rule, 4n plus 2 pi electron systems are having aromatic in nature. So, here if you look at the first example, we will look at the pyrrole unit. So, each pi bond constitutes or corresponds to 2 pi electrons. So, here we have 2 pi electrons and there are 2 pi bonds are there. So, 2 plus 2 pi total equivalent to 4 pi electrons are there. but this is not actually having 6 pi electrons. So, how do we reach the 6 pi electrons? So, nitrogen is having one lone pair, and this lone pair also participate in the aromatic pi sextet formation. That means 6 pi electron formation. So, 4 pi electrons from the pi bond and one lone pair of electron altogether leads to 6 pi electrons for the pyrrole ring. Similarly, when we talk about furan, furan has two lone pairs. So, one of the lone pair participate in the pi electron cloud formation. Similarly, in the case of sulfur also, one of the lone pair participates in the pi electron cloud formation. So, total we get 6 pi electrons. So, in furan also we will get 6 pi electrons. So, this is the second criteria. That means all these compounds have 4n plus 2 pi electrons. They obey the Huckel's rule. So, this is the Huckel's rules. So, the first criteria is the planarity. The second one is following Huckel's rule. And let us look at the third one, which is having the ring current in the aromatic systems. If we look at isolated double bond, this hydrogen, this olefinic hydrogen resonates at 5.6 ppm, but when there is a pi electron cloud, that pi electron cloud generates a ring current, and that ring current deshields this proton. This deshielding of hydrogen atom, in the case of benzene ring, these protons are actually downfield shifted due to the presence of pi electron. The pi electron actually generates the ring current, and there is a small magnetic field because of this ring current, and that deshielding of proton. So, that is the reason these appear at a downfield. So, at 7.3 ppm, aromatic protons appear for the benzene, whereas for the isolated double bonds where there is no pi electron cloud and there is no ring current, they appear at 5.6 ppm. And if we extend the same, the pyrrole has two protons. One of the alpha carbon's proton appear at 6.73 and the beta one appear at 6.23 ppm. This is much higher than the 5.6, which is for the isolated double bond, although it is a little less than the benzene. So, it still says that this pyrrole is having a ring current, and because of that these protons are appearing at the downfield region. And if you look at furan, the orthoproton comes at 7.4 ppm and the beta carbon's proton come at 6.38 ppm. In the case of thiophene, that appears, the alpha carbon's protons appear at 7.33 and the beta carbon's proton appear at 7.12 ppm. So, all these things represent that there is a pi ring current in the case of heterocycles, and this is also one of the criteria to show aromaticity. And of course, when we talk about the reactivity, this is a cyclopentadiene. These two double bonds are in conjugation, but there is one carbon which is a sp3 hybridized carbon. So, that means not all the carbons are actually sp2 hybridized carbon. So, that is the reason this is actually considered as a just two double bond, that is diene. It is considered as a simple diene. So, because this is a simple diene, this undergoes addition reactions, say for example Diels-Alder reactions and addition across the double bond. All those things happen in the case of cyclopentadiene. But when we talk about heterocyclic compounds, especially the 5-membered pyrrole, furan and thiophene, they do not undergo addition reaction. That means this double bond and this double bond, these two does not behave like a diene type double bond, but they are involved in the aromatic ring formation. So, that is the reason, similar to benzene, these compounds undergo substitution reaction very readily compared to addition reaction. So, this is a major difference, and we can also say that these 5-membered heterocycle are having the aromatic nature. That is why they are undergoing substitution reactions rather than addition reactions. Of course, there is one simple exception. Furan at some times can undergo Diels-Alder reaction also, and that actually shows or behaves like a diene type compound. So, that is the only exception in the case of furan, but pyrrole and thiophene actually undergo substitution reaction much similar to benzene or an aromatic system. The next one is the thermodynamic stability of these compounds. From the heat of hydrogenation, we can say that these compounds are having thermodynamic stability which is close enough to benzene, and they also have stabilization energies. For example, when we talk about the aromatic stabilization energy, benzene is having a very high value of 38, whereas 38 kilocalories per mole, and in the case of thiophene, furan and pyrrole, they actually have some amount of aromatic stabilization energies, whereas cyclopentadiene does not have this one. That means these two double bonds behave like double bond only. There is no cyclic delocalization or similar things what is seen in the case of pyrrole, furan or thiophene. And similarly, when we look at the heat of hydrogenation, the cyclopentadiene has a very high heat of hydrogenation. That means they undergo addition reactions. So, that means the double bond nature is quite different compared to thiophene, furan or pyrrole, because they have lower heat of hydrogenation. So, that means they are much more reactive compared to cyclopentadiene. And if we look at all the compounds, we can recollect what we have seen. All these compounds are having pentagonal structure. That means furan, pyrrole and thiophene are 5-membered heterocycles. They have a pentagonal or the planar structure. And here the heteroatom and the carbon, all of them are sp2 hybridized. So, this is the major requirement for the planarity, and each ring has 2 sp2 sigma bonds and 1 sp2s sigma bond, that is for the hydrogen, because here we have actually every carbon has one hydrogen atom. So, this CH bond is actually formed by the sp2s sigma bond formation, and this carbon has a bond with the neighboring carbon atom, because there are two bonds are formed here between these two carbon atoms. Those are the sp2 hybridized bonds, and there is also one bond with the heteroatom here. So, this is also a sp2 hybridized sp2 hybridized sigma bond. So, these are all the different types of bonds that are formed in these kind of heterocycle compound, and along with that there is one pz orbital, and that is responsible for the pi bond. So, this sp2 hybridized sigma bonds are formed, and the p orbital is responsible for the pi bond formation, and the nitrogen, oxygen and sulfur, they have one lone pair participated or involved in the aromatic sextet formation, and the second lone pair on oxygen and the sulfur are actually perpendicular to the pi system. So, those two electrons are not involved in the pi electron ring formation. That is the reason if we look at the oxygen and sulfur, there are two lone pairs are there. So, total 4 lone pair electrons are going lone electrons are going to be there, and there are 2 pi bonds. So, again there are going to be 4 pi electrons are going to be there. So, total if we look at, there is going to be 8 electrons will be involved in that system, but for the according to the Huckel rule we only require 6 pi electrons will be aromatic in nature, and when there are 8 pi electrons, that is actually going to be anti-aromatic in nature. So, that means one of the lone pair, that means out of the 2 lone pair, only one is involved in the aromatic pi sextet ring formation, and the other 2 is actually perpendicular to the sp2 or the pi electron cloud. That is the reason that is not involved. So, we can actually say here only one of the lone pair from oxygen and sulfur are involved in the pi ring formation. So, how do we see that? We can visualize the same thing here. If we look at the pyrrole ring, there are one electron in the pz orbital. So, this pz orbital all form the pi orbital or the pi system of this ring structure, and 2 electron from the nitrogen is involved, one pi electron, one p orbital electron from 4 carbon atoms. Here we have 1, 2, 3 and 4 carbon atoms contribute 1 p electron. So, that means 4 plus 2, total we have 6 pi electrons. So, that is why this actually forms the aromatic pi ring system. And if we look at the other 2 heteroatoms, that means when the X is oxygen or sulfur, they have 2 lone pairs. So, out of the 2 lone pairs, only one lone pair is involved in the pi ring formation. That means the 6-membered 6 electron pi aromatic system formation. The other 2 electrons are actually perpendicular to this system. So, that is the reason these 2 electrons are not involved. So, that is the reason we do not have 8 pi electrons. In the case of oxygen and sulfur, we only have 6 pi electrons. So, this is how we can actually visualize how they form the aromatic ring system. And when we look at cyclopentadiene, the cyclopentadiene, as we have seen earlier, is having a sp3 hybridized carbon. That means this is a CH2 carbon. So, this compound is not going to be planar. These sp2 hybridized carbon atoms are actually planar in nature, but this particular is a tetrahedral one. So, when it is a tetrahedral one and these are actually planar one, the entire molecule is not going to be planar in nature. So, that is the reason cyclopentadiene is not a aromatic system. But when we talk about the cyclopentadienyl anion, this is going to be a sp2 hybridized carbon. So, that means we now have all the carbons which are sp2 in nature. So, that means this compound is actually planar in nature. And here we have 2 electrons from this sp2 hybridized carbon. That means this is having a negative charge. So, this will contribute to 2 electrons, and there are 4 electrons from the 2 pi bonds. So, this is 2 pi and here again another 2 pi. So, 2 plus 2 plus 2, total we have 6 pi electrons, and this cyclopentadienyl anion is now going to be aromatic in nature. And similarly, if we compare the same with the pyrrole and furan, we have already seen these 3 systems are also aromatic in nature. We can actually draw various resonance stabilized structures for the delocalization of the electrons in the heterocycles. Let us first look at the pyrrole system. The pyrrole lone pair is actually now coming towards the ring, and these 2 pi electrons are now shifted towards this particular carbon atom. So, this carbon atom now develops a negative charge, and this nitrogen is now having a positive charge. So, as we have seen earlier, the nitrogen heterocycles can have either positive charge, neutral or negative when they are present in the cyclic system. So, here we are having a positive charge for nitrogen, and in this system we have a neutral nitrogen. So, the shift of pi electron actually takes place, leading to a negative charge on this particular carbon. And similarly, we can also write the other structures. So, if we look at very carefully, all the 4 carbon atoms, let me number this as 1, 2, 3, 4. All the 4 carbon atoms are having negative charge. So, in this particular case, we have the second carbon having a negative charge. This is the 4th carbon, this is the 1st carbon, and this is the 3rd carbon. So, in the pyrrole ring structures, all the 4 carbons are actually having negative charge. The reason why we have to know about this is when they undergo basically the electrophilic addition reactions, then we will see which position the reaction will actually occur. So that can be easily explained based on these kind of resonance structures. When we look at furan, furan also can be undergoing the resonant delocalization similar to pyrrole. So one of the lone pair comes into the ring, and we can draw the similar structures how we draw for pyrrole moiety. So here again the oxygen is having a positive charge, and one of the ring carbon is having a negative charge. When we extend to the same, we can also draw the similar resonance structures for thiophene also. Thiophene, the sulfur has a positive charge, and the carbon, one of the ring carbon here, has the negative charge. So similar to pyrrole, furan and thiophene can also have various resonance stabilized structures. So this delocalization actually pushes the negative charge on all the carbon atoms, but not on the hetero atom. So this is the one thing we have to remember. So that's the reason whenever the electrophilic substitution reaction occurs on the heterocyclic ring, it is the ring carbons which actually undergo the reaction because they are having negative charge. And if you look at the dipole moments, the cyclopentadiene has a dipole moment of 0.42, whereas pyrrole, furan and thiophene have a little bit higher dipole moment. So this is because of the introduction of the heteroatom. When there is a carbon in the case of cyclopentadiene, only this particular part, which is electron rich in nature, is pointing, the dipole is pointing towards this pi bond, that means towards the ring, whereas this carbon is not having that charge. So that is the reason the dipole is pointing towards the ring, and the value is going to be 0.42. And when we look at the heteroatoms, we know the heteroatoms are actually electron withdrawing in nature. So that means they are more electronegative compared to carbon atom. So they generally pull the electron towards itself. So that is the reason if you look at oxygen and sulfur, the dipole is pointing towards the heteroatom because they are much more electronegative or pulling electron towards itself compared to carbon atom. So they pull these pi electrons towards themselves. That means the charge polarization is away from the ring towards the heteroatom. That is how the dipole moments are appearing in the case of furan and thiophene. And furan is having 0.70 d by unit, and thiophene is having 0.51 d by unit. Because the sulfur is a huge atom compared to oxygen, there is a distribution or a diffusion of the charge on the various orbitals. So that is the reason oxygen is having a much more higher dipole moment compared to thiophene. But when we look at the pyrrole, this is a very unique case. Although we have a heteroatom, that is nitrogen, which is present, which is actually more electronegative than carbon. So we expect the the dipole moments to be polarized towards the heteroatom, but unfortunately what we see is pyrrole is having a very high dipole moment, and that too here the dipole is towards the ring and not towards the nitrogen atom. So what is the reason? Because the reason is simply because the lone pair of the electrons on the nitrogen are actually coming towards the ring, forming the aromatic system. So when there is an aromatic system, what actually happens is the nitrogen is no longer having the lone pair on it. In other words, nitrogen is having the positive charge. So that is what we have seen in the earlier delocalization structures. So when the nitrogen is having a positive charge, now this is the place where more electron density is present. In other words, towards the ring all the electrons are flowing. So because of that, in the case of pyrrole, there is a huge negative charge towards the ring, that is why it is having a very high dipole moment, and nitrogen is having a positive charge, so that is the reason the dipole is pointing towards the ring and not towards the nitrogen atom. So whenever we write the dipole moments, this arrow points towards the more negative part. So whatever is the most negative part, the arrow is pointing towards that end, and then the other end is given like this plus like symbol here. So using that same convention, we can actually say in the case of pyrrole, the ring is having more pi electron because the nitrogen donates its lone pair towards the aromatic ring, aromatic 6 pi electron formation. So this is actually explained based on the electronegativity difference. But if we go to the saturated one, that is pyrrolidine, tetrahydrofuran and tetrahydrothiophene. So these are all the three systems. In these systems, if you look at, there is no delocalization of electrons. So in other words, the nitrogen retains its lone pair, oxygen retains its lone pair, sulfur retains its lone pair. So that is the reason the electron pole is towards the heteroatom only, and that is the reason in the case of pyrrolidine there is no pi electrons in the ring, and the nitrogen is the only thing which is having the negative charge. It is more electronegative than the carbon, so it pulls the electrons, the sigma bonded electron also towards itself, making this side of the ring, that is towards the heteroatom, the dipole is polarized. And because of the difference in the electronegativity between carbon and nitrogen, pyrrolidine is having a higher dipole moment, that is 1.33, tetrahydrofuran having 1.75, tetrahydrothiophene having 1.85, because here we have two lone pairs on the oxygen, so due to which two lone pairs on the sulfur, due to which the dipole moments are much higher for furan and thiophene. So what we can say overall is, when we talk about the sigma framework, that is inductive effect, it is a very weak one. This actually acts towards the heteroatom, and when it is a pi framework, because we talk about the pi electron cloud which is involved in the dipole moment, since there is a higher pi electron density within the ring or towards the ring, this is having a very strong effect, or it is a mesomeric effect, due to which the charge dispersion, that means the dipole's direction changes based on whether we talk about pyrrole, furan or thiophene, and pyrrolidine, tetrahydrofuran or tetrahydrothiophene. So as we can see, the sigma framework where the inductive effect is a very weak one, in the case of pyrrole there is a positive charge, and if you look at the pyrrolidine, the dipole moment of pyrrolidine is much lower. So in other words, what we can say is oxygen involves inductive effect, whereas the nitrogen gets involved in the resonance effect. So when we talk about the resonance energies, benzene is having a highest resonance energy of 152 kilojoules per mole, and the carbon is also having a lower electronegativity. So if you look at the order of aromaticity, this is having a highest resonance energy. So this is highly aromatic in nature. That means the reactivity of these compound, that is benzene, is going to be much lower, because it is going to be much stabler because of the higher resonance energy. And if we compare the same with the thiophene, pyrrole and furan, we can actually say that thiophene may be more reactive, pyrrole is again more reactive, furan is also reactive when we talk about reaction. So we will also look at what is the order of reactivity. Let us look at the difference in the bond length between benzene and other heterocycles. Generally, the CC single bond is actually 1.54 angstrom, whereas CC double bond is 1.33 angstrom. Because of the resonance, we have a in between a bond length. That means it is neither a single bond nor a double bond. So 1.39 angstrom is the bond length of carbon-carbon bond length in the case of benzene, whereas in the case of thiophene, furan and pyrrole, we have different bond length due to different nature of the bond. So this is actually a single bond. If we look at the normal single bond, it is 1.54 angstrom, whereas in the case of thiophene, furan or pyrrole, the bond, this particular bond, which is actually the single bond, is much lesser in length. That is due to the delocalization of the pi electron. So partially this bond also behaves like a double bond, and similarly this double bond is having a little longer bond length. The actual CC double bond isolated bond length is only 1.33, but thiophene, furan and pyrrole have a much higher CC double bond length. This is due to the partial single bond nature of this particular bond. So that is the reason we can say there are varied bond length for these kind of compounds, and of course the heteroatom carbon bond length varies depending on the electronegativity of the particular heteroatom. And if you look at the electron densities, in the case of benzene, the electron density across all the carbon atoms are very same, or we can say it is unity. So all the carbon have uniform electron density because there is a delocalization. That is the reason all are having the same electron density. But when we look at thiophene, furan or pyrrole, the electron densities are different. Actually, if we look at in the case of sulfur, we have to have the electron density 2, and this carbon should have the electron density 1. So this is what is the expected value, but this alpha carbon is having a higher electron density than 1, and this beta carbon is also having higher electron density than 1. So what does this imply? Actually, instead of 2 electrons on the sulfur, some of the electrons are actually given to the ring. That is why these carbons are getting more electron density than 1. So if we add all these three things, so then we actually will end up with a total of 6, because there are total 6 pi electrons are there. So we can say here we have 6 carbon, all carbon have 1 as the electron density. So 6 into 1.0 is equal to 6 pi electron density. So this is what we can easily calculate for benzene. Whereas when we talk about thiophene, the sulfur is having only 1.76 instead of 2. So we have 1.76, and there are 2 carbon atoms which are having the electron density 1.071. So we have to multiply 2 into 1.071. Then again 2 carbons which are having the electron density more than 1, that is 1.06. So we again have 2 into 1.046. So if we multiply these values, so 2 into this value is 2 point, this is 092, and when we multiply this one, this is going to be 271 is 241. Then we have 1.76. So if we add these numbers, what we are going to get is actually going to be 6.0. So 2 plus 2 4, 4 plus 6 0, then we have 1, 9 plus 4 13 plus 7 0, then we add the 1. So 7 plus no, this is actually let us ignore the last digit, we will only calculate the first 2 digits. So 9 plus 413 plus 6, it is going to be 9. So we have 1. So 7 plus 1 8 plus 1 9, then 2 plus 2 plus 1 5. So instead of 5, we are coming close to 5.99, we can assume that this is going to be 6. So in other words, the 6 electrons are distributed like 1.76 on sulfur, 1.071 on this carbon, this is the alpha carbon, let us say, and 1.046 on the beta carbon. So if you look at this, this actually tells one more additional information. So when the reaction occurs on thiophene, which of the carbon is having more electron density, that is more prone to undergo reaction, especially the electrophilic substitution reaction, because electrophile is having electron positive charge. So that means it is seeking electrons, and which of the carbon is having more electron density can easily donate it. So that means between alpha and beta carbon, this alpha carbon is having a higher electron density, so the reaction will occur very readily at the position 2. Similarly, if we extend the thing for the furan, here again this is having 1.078, so that means this place is more prone to undergo electrophilic attack. But when we come to the pyrrole, actually this carbon becomes more electron density. So that means the 3 substitution is more prone in the case of pyrrole compared to 2 substitution. Of course, if see the difference, this is only 0.003 electron unit difference only is present. So that means equally 2 and 3 substitution may happen, and it may be towards the 3 substitution as a major one. That is the case of pyrrole's reactivity. So based on the electron densities also, we can actually find out how they actually undergo reaction. And if we extend the same calculation what we did for thiophene, the oxygen is having a lesser electron density, and if you look at nitrogen, nitrogen is having even much lesser electron density. Instead of 2.0, this only has 1.65. So that means this nitrogen is actually having a positive charge at most of the time. So that is what we can actually infer from this electron densities, and this is also a good way to understand how the pi electron, that is the 6 pi electrons, are distributed within the heterocyclic system. And as we have talked about the relative reactivities, that means resonance and the inductive. So we have a different electron density on the heteroatoms. Because of the different electron densities, the reactivity is also going to be different. So that's what we say in the case of benzene, it is having only one electron which is distributed throughout the system in a uniform way. So that means there is no selectivity in the case of benzene. Any carbon can be attacked by the electrophile. So when the electrophile attacks the carbon, especially the benzene ring, it can attack this place or this place, whatever the place it attacks, it is actually uniform. Whereas in the case of heterocycles, they attack at a different place. That depends on the pi electron densities. That's what we have seen. So here the sulfur is having 1.76 electron density only. Oxygen is little bit less, but nitrogen is much less. So in other words, how the reaction actually works can be explained based on the inductive effect as well as the resonance effect, because so far we have only talked about the resonance effect, which is responsible for the reactivity. Of course, there is one more effect called the inductive effect. So using this resonance effect, we can explain the reactivity difference between 2 and 3 carbon. So whichever is leading to a stable intermediate, then the reaction actually occurs. That can be explained using the resonance effect. In other words, the electron density can be used to explain the observed product formation. And when we talk about the inductive effect, that actually tells why pyrrole is more reactive than thiophene or furan. So this is also another reason. The inductive effect is the one which actually tells why furan is more reactive, because we know this particular nitrogen is having much less electron density, whereas the carbons are having more pi electron density. That is the reason they undergo the reaction much faster compared to furan and pyrrole. So this inductive nature can be used to explain the different reactivity of furan, different reactivity of pyrrole with furan and thiophene. Of course, we cannot always say the resonance and the inductive effect. Depending on the reaction conditions also, the product formation or the product distribution varies. So, here some of the examples given, and based on the stability of the intermediate, what we can say is thiophene and furan forms stable intermediate when they undergo electrophilic substitution, and in the case of pyrrole it forms a highly stable intermediate. So, that is the reason the reactions of pyrrole are much faster. Let us look at the 6-membered heterocycle, that is the pyridine one. We will just look at the structure of pyridine. Pyridine is having a planar structure very similar to thiophene, pyrrole and furan. This 6-membered ring is also planar in nature. So, that means this is one of the criteria for the aromaticity, and similar to pyrrole and furan, what we have seen is like there are two sp2 sigma bonds and one sp2s sigma bond formed in these cases, and we have also seen earlier that pyridine is not having a hexagonal symmetry similar to benzene. So, how do we know it is not having the hexagonal symmetry? The thing is like we can actually find out from the different bond length. So, in the case of benzene, we have uniform bond length for all the carbon atoms, but in the case of pyridine, we have different bond lengths. So, that means there is no hexagonal symmetry possible in this particular system. If you look at the bond between these two carbon atoms, this is 1.392 angstrom unit, and between carbon and nitrogen, if you look at it, is only 1.338 angstrom unit. So, that means there is a difference between the bond length, which tells that this compound is no longer hexagonal in nature. And of course, if you look at the bond angle also, in the case of pyridine, we have all the bond angles at 120 degree. In the case of pyridine, the bond lengths are quite different. So, this particular bond length is around 118 only. Similarly, this bond length is 118, whereas this carbon and the heteroatom, this bond length is 124, which is higher than the 120 normally seen in the case of benzene, and this particular bond length is only 117. So, that means we also have a non-uniform bond length in the case of pyridine. So, these are all the difference between pyridine and benzene. So, in the case of pyridine, one of the electrons in the p orbital is involved in the 6-pi electron ring formation, and the lone pair on nitrogen is actually perpendicular to the pi electron cloud. So, that is the reason these two electrons are not involved in the pi ring formation, and because of this reason pyridine is basic in nature, because this particular two electron, that is the lone pair, is available, and the nitrogen can now behave like a base. In the case of pyrrole, those two electrons are involved in the 6-pi electron formation. So, pyrrole is not a basic compared to pyridine, since the pyridine has this lone pair electron perpendicular to the pi electron system. So, this acts as a much better base. And as we know, pyridine shows aromaticity. So, it is also having the ring current. From the NMR, we can actually find out the hydrogen atoms are appearing at a downfield, like the ortho hydrogen appears at 8.5 ppm and the para appears at 7.5 ppm and the meta one appears at 7.1 ppm. So, that is the reason we can say there is a strong pi electron current present in the case of pyridine ring. And as we know, the reactivity of pyridine is quite different from dienes, because these double bonds are not isolated double bonds, but the resonance involved double bonds. So, that is the reason they behave very similar to benzene system. So, pyridine undergoes substitution reactions rather than addition reactions. And when we talk about electrophilic aromatic substitution, benzene behaves or benzene reacts faster than pyridine. So, when we talked earlier, the that's in the case of 6-membered heterocycles, these rings are actually pi deficient. That is what we have seen. So, when the ring is pi deficient, the presence of nitrogen actually pulls the electron towards itself because of its electronegative nature. That makes this ring undergo electrophilic aromatic substitution at a much slower rate. In other words, benzene, which is not having this heteroatom, is having much more pi electron within the ring, so it undergoes electrophilic substitution very readily, but nitrogen pulls the electron away from the ring system, so that makes this ring system already pi deficient. Because of pi deficiency, electrophilic reactions, electrophilic aromatic substitution reactions occur very slow in the case of pyridine. But on the other hand, because it is a pi deficient in nature, now a nucleophile can easily undergo or attack this benzene system. So, that is the reason pyridine actually undergoes nucleophilic aromatic substitutions far better than a benzene system. So, this is how we can understand the pyridine's aromaticity. And if we look at the resonance structures, pyridine, we can draw various resonance structures for pyridine. The structure 1 and 2 are the neutral structures where simple bond rotation, that is delocalization of the double bond alone, is shown here. And in the case of other three structures, structure 3, 4 and 5, we have a charge separation. There is a negative charge on nitrogen, there is a positive charge on one of the carbon atoms. So, that is the reason there is a huge separation of charges. So, nitrogen is having a negative charge, the ring is having a positive charge. Due to this difference in the charge separation, the dipole moment of pyridine is much higher than piperidine, because here we have 2.3 dB for the pyridine, whereas piperidine has only 1.2. So, the presence of resonance actually increases the dipole moment of pyridine. And as we know, one of the ring is not involved in the 6 pi electron cloud formation. This is available for the this is present perpendicular to the ring system. So, that is the reason this is pyridine is basic compared to pyrrole. Let us recap in the summary what we have studied so far. We have studied about the various criteria of the aromaticity. So, whether the 5-membered heterocycles and the pyridine are planar in nature or not, we have seen, and what is the 4n plus 2 pi electron rule, and what are the ring currents where the protons appear, all those things we have studied. We have also studied about the resonance contribution or the various resonance structures of pyrrole, thiophene and furan, where the charge lies, especially the positive charge on nitrogen or the oxygen or on sulfur, all those things we have seen. And we have also studied about the various general characteristics based on the aromaticity, like what is the reactivity, what is thermodynamic stability, what are the dipole moments of various heterocyclic compounds, especially furan, pyrrole and thiophene, and what are resonance energies in comparison with benzene, what are the different bond lengths, what are the electron densities on each carbon atom and on the heteroatom, and how this difference in the electron density is affecting the reactivity of various positions. That means when the electrophilic substitution happens, how the reactivity changes between position 2 and 3, all those things we have studied. We have also studied about the dipole moment, how the dipole moment varies between pyrrole and furan and thiophene with respect to cyclopentadiene, all those things we have seen. With that, we conclude this session. Thank you.